Sort colors. We will make the question clear first, then build the one-pass idea together. Before touching the pointers, let us pin down exactly what the problem wants. The input is nums equals 2, 0, 2, 1, 1, 0. Every entry is either 0, 1, or 2. Rearrange this same array so all zeros come first, then the ones, and finally the twos. We are not allowed to hide the work behind a library sort. For this example, the finished array is 0, 0, 1, 1, 2, 2. That array is the answer. We are not returning indices, counts, or a second array. The input itself must end in this order. Now give those numbers a visual identity. 2 is blue, 0 is red, and 1 uses the light middle color. The number remains printed inside every tile, so the logic never depends on color alone. Reading left to right, this is still the original array. 2, 0, 2, 1, 1, 0. Here is the target again, this time as 3 clean groups. The 2 zeros occupy the left group, the 2 ones sit in the middle, and the 2 twos finish on the right. So the final array is 0, 0, 1, 1, 2, 2. The remaining question is how to reach it in one pass. A general sort works, but it spends O of n log n time solving a more general problem than we have. Counting zeros, ones, and twos is linear, although it needs one pass to count and another to rewrite the array. Because there are only 3 categories, 3 pointers can partition the array in one pass and constant extra space. The key is not memorizing 3 pointer names. It is knowing what each region already guarantees. Everything before low is confirmed to be 0. From low up to but not including mid, every value is confirmed to be 1. Mid through high is still unknown. Mid always points to the next value we must classify. Everything after high is confirmed to be 2. Once the unknown region disappears, the job is done. Suppose mid lands on 0. 0 belongs at the left edge of the unknown region, exactly where low is waiting. Swap the values at low and mid. That locks one more 0 into place. Both positions are now understood, so low and mid each move one step to the right. A 1 is the easy case. It already belongs in the middle partition. There is nothing to swap. Accept it where it is and move mid forward. Low and high do not move because neither outer partition gained a value. When mid sees 2, send it to the far side of the unknown region by swapping with high. The 2 is now confirmed on the right, so high moves left, but mid does not move yet. The value that just arrived from high has never been checked. This is the detail interviewers often ask about. High still belongs to the unknown region before the swap, so the value coming back to mid could be 0, 1, or 2. We cannot skip over it. Keep mid in place, shrink high, and let the next iteration classify that incoming value. At the start, nothing has been classified, so the entire array is unknown. Place low and mid at index 0 and high at index 5. Keep going while mid is at or before high. That condition simply means the unknown region is not empty yet. Mid is looking at index 0 and it finds a 2. That 2 belongs on the right. Swap indices 0 and 5. The array becomes 0, 0, 2, 1, 1, 2. High steps left to 4. Mid stays at 0 because the value that arrived there still needs an inspection. This time mid sees 0 at index 0. That 0 belongs at low, which is index 0. Low and mid already point to the same tile, so the swap changes nothing. The 0 is still confirmed in the correct place. We have classified that position, so low moves to 1 and mid moves to 1. This time mid sees 0 at index 1. That 0 belongs at low, which is index 1. Low and mid already point to the same tile, so the swap changes nothing. The 0 is still confirmed in the correct place. We have classified that position, so low moves to 2 and mid moves to 2. Mid is looking at index 2 and it finds a 2. That 2 belongs on the right. Swap indices 2 and 4. The array becomes 0, 0, 1, 1, 2, 2. High steps left to 3. Mid stays at 2 because the value that arrived there still needs an inspection. Mid now sees 1 at index 2. 1 already belongs in the middle. No swap is needed here. Just move mid forward to 3 and keep both outer boundaries where they are. Mid now sees 1 at index 3. 1 already belongs in the middle. No swap is needed here. Just move mid forward to 4 and keep both outer boundaries where they are. Mid has crossed high, so there is nothing left to classify. The input array is now 0, 0, 1, 1, 2, 2, zeros, then 1s, then 2s. Every inspection shrinks the unknown region. That gives O of n time and O of 1 extra space. Here is a clean way to explain the solution in an interview. Low, mid, and high divide the array into confirmed zeros, confirmed 1s, an unknown region, and confirmed 2s. A 0 swaps with low, then both low and mid advance. A 1 is already in the middle, so only mid advances. A 2 swaps with high. High moves left, but mid waits to inspect the incoming value. When mid passes high, the unknown region is empty and the array is sorted. Start low and mid at the left edge and high at the right edge. Initially, the full array is unknown. Continue while mid is at or before high. Each iteration classifies at least one position. Swap 0 with low, then move both low and mid because that position is fully classified. Swap 2 with high and move only high. Mid stays because the incoming value has not been checked. A 1 already belongs in the middle partition, so no swap is needed. Move mid forward.